Hello and welcome back to the second video of the YOLO series. In this video, we'll be introducing the YOLO algorithm in the first section. And second, we will be talking about why the YOLO algorithm is useful and its applications. And on the third section, I will talk about the history and the milestones achieved by the YOLO algorithm. And on the fourth section, we will talk about the applications of YOLO in the computer vision industry. And on the fifth section, we will talk about other competitors of YOLO algorithm. And on the last section, we will talk about the key insights for this algorithm. So let's start off by talking about what YOLO stands for. So YOLO stands for You Only Look Once, as we have previously seen in the first video. And the name comes from the fact that the algorithm only pays attention to a specific point, or as you might say, a specific part of the image in order to make its predictions. And YOLO is a regression algorithm that falls under the class of real-time object detection. So emphasis on the keyword real-time. We will be looking at why we call it a real-time object detection later on in this video, with a multitude of computer vision applications. So YOLO combines what was once a multi-step process using a single neural network to perform both classification and prediction of bounding boxes for detected objects. So what do we mean by a multi-step process? So there are other families of object detectors such as RCNN, and they are a multi-step convolutional neural networks. That means they don't just use a single convolutional network, so they use a multi-stage process. So the first one might be the feature extractor, and the second one might be the classifier or the prediction of the bounding boxes. So as such, it is heavily optimized for detection performance and can run much faster than running two separate neural networks at the same time to detect and classify objects separately. So the RCNN family, we need to train the network 2 times. So first we have to train and optimize the feature extractor model. And on the second part, we have to fine-tune the classification model. So we have to train the model 2 times, and the fine-tuning process takes a long time. And YOLO just uses a single backbone or a single convolutional network to do the entire processing of the image. So the creators of YOLO, one of the famous creator of YOLO is Joseph Friedman. He's the creator of the most popular YOLO network. He also maintains the DarkNet neural network framework, and as we will take a look at in the next video, DarkNet is the backbone of the YOLO architecture in itself, and he's the corresponding author of the papers starting from YOLO v1 up until YOLO v3. So YOLO v1 was the first paper initially written by him and his supervisor, and the second paper was YOLO 9000, better, faster, and stronger. It's also known as YOLO v2, and finally we have the YOLO v3, which is an incremental improvement from the YOLO v2 model. However, in February 21, 2020, Joseph Friedman tweeted that he had ceased his computer vision research to avoid enabling potential misuse of the tech, citing in particular military applications and privacy concerns. So he didn't want to continue contributing to the computer vision research because he he feared that there might be a misuse of this kind of technology in military applications. So, starting from YOLO v4, Alexei Bukovsky is a research engineer with 6 years of experience in machine learning and over 16 years of experience as a C++ developer. He picked up the slack from YOLO v4 and also contributed on the scaled YOLO v4 paper. And now he also released the YOLO v7 paper. So he specializes in PyTorch, C++, and DNN framework, darknet, as well as developing state-of-the-art neural network as a backbone for YOLO v4 and scaled YOLO v4. And this object detector is now being utilized by the Taiwan government, BMW, Innovation Lab, Amazon, and other companies. So when we started the video, we said that YOLO is the detection model. So what do we mean by object detection? So before we look at what object detection is, we have to define the terms classification, localization, and finally object detection. So given an image with just one object, we tell what kind of the object it is. So for example, if you have an image with a cat, then you can just say that this is a cat. And if you have another image with a dog, then you just say it's a dog. So we're not concerned about the position of that object within the image. We just classify the object with labels. So another concept is, besides just giving labels to the entire image, why don't we specifically locate a single object inside that image? So let's say if you have a cat inside an image, instead of just saying that the whole image is a cat, we can localize which part of the image or which pixels in the image signify a cat, and we put a bounding box in the position of the cat. So that's called localization. And the third one is object detection. So it's often it's often confused with localization. But object detection is just localization for multiple objects. So if you have multiple instances of a class or different instances inside the same image, then we can call it object detection because we're locating and labeling all of the objects inside the image. So why is YOLO useful? So first, it improves the detection time, given that it predicts objects in real time. So one of the advantages of YOLO over the other object detectors is that it's very fast. And since it's based on a single neural network, it's very easy to train on a GPU. So it's basically deployed in embedded computing area or with someone it has a higher efficiency in computation. So it's preferred in places where you just want a compact model that gives you accurate predictions. So initially, YOLO doesn't give accurate results as the other family of networks in object detection, but now it has evolved so much that it's being the preferred model being deployed in these kinds of applications. So It also gives minimal background errors. And finally, the algorithm has wonderful learning capabilities that enables it to learn the representations of objects and implement them in object detection tasks. In this section, we will look at the timeline of YOLO, starting from its inception right until now. In 2016, YOLO v1 was released, and it was the first fully convolutional network for object detection. In 2017, we have the release of YOLO v2. The version earned the honorable mention at the CVPR 2017 because of its significant improvements on anchor boxes and higher resolutions. In 2018, YOLO v3 was released, and it improved the performance on detecting small objects because of the ability to run predictions at 3 different levels of granularity. And in YOLO v1, we just had a single detection on the final layer. But starting from YOLO v3, and it wasn't really good at detecting smaller objects and detecting objects at different scales. So in YOLO v3, they optimized the model of YOLO v2 because in YOLO v2 we have anchor boxes. And after the introduction of anchor boxes, we have predictions at different stages. And on those stages, we have a different scale of images in which we can perform detections. So we have YOLO v3 has 3 different levels of detection. So we have the first detector is like for smaller objects, for medium-sized objects, and also for large objects. And this is like the major improvement introduced in YOLO v3. So we will look at the major improvements that have been made in YOLO v3 in that particular section. In April 2020, YOLO v4 was released, and starting from YOLO v4, we have Joseph Redman wasn't working on YOLO after YOLO v4, so we have Alexei Bukovsky, who introduced novel improvements and also used for the first time the mesh activation function, and also improved the feature aggregation process. So the mesh activation function is actually a different kind of activation function. And in the next video, we'll see the activation function in detail so that we can really understand what's happening there. And in 2020, YOLO v5 was released, but it wasn't released by Alexei Bukovsky. It was released by a company called Ultralytics. And it doesn't have an official paper, but it has a source code. And it also introduced novel improvements on the architecture itself. So those are the major milestones of YOLO, but in recent times, we have different versions of YOLO that have been released since 2020. And we have PP YOLO, which is also known as Paddle Paddle YOLO, which was released in July 23rd, 2020. And in November of the same year, we have the Scaled YOLO v4, which was released by Alexei Bukovsky again. And this paper is also called Scaling the Cross-Stage Partial Network, which is the CSP backbone was scaled, which was originally used in YOLO v4. And when we talk about the backbone architecture, we'll talk about the cross-stage partial network in detail. And in 2021, we have the YOLO R. The R stands for representation, and instead of using the entire name for YOLO, they just came up with their own acronym, which is you only learn one representation. And it's an entirely different architecture, and we will also look at the YOLO R. And in July 18 of 2021, we have YOLO X, which is an anchor-free version of YOLO. So we've talked about the anchor boxes being introduced in YOLO v2, but in YOLO X, they actually said that they don't need the anchor boxes, and they also modified the architecture so that we can make better predictions without the anchor boxes. And finally, in this year, in July 6, 2022, YOLO v7 was released by the original author of YOLO v3, Alexei Bukovsky, which surpasses all known object detectors, both in the YOLO family and the regional based convolutional neural networks. So this particular YOLO model is the state of the art in both speed and accuracy. So what are some of the applications of YOLO? So YOLO is being used for autonomous driving. Object detection is required to avoid accidents on the road since there is no human managing the wheel. In this case, it helps to detect people, cars, and any external hazards appearing on the road. And it can also be utilized for wildlife detection so that it's applicable for trees and biodiversity as it is for different species of animals to track their growth and migration. And even in robotics, depending on the industry the robot operates in, some robots do require computer vision to detect objects on their paths and perform a particular instruction. And in retail, when we perform a visual product search or reverse image search, which are becoming increasingly popular in websites like Amazon and other applications, which wouldn't have been possible without object detectors like YOLO. So what are the other object detectors? So what kind of algorithms are out there besides the YOLO algorithm? So one of the earliest object detector was the histogram of oriented gradients, and it is one of the traditional object detection method, which was first introduced in 1986. And the current HOG uses like a feature descriptor, and it doesn't even utilize a neural network to detect objects of interest. While being revolutionary in the beginning, this method is very time-consuming for complex computer vision tasks. And the RCNN family, and we will just take a look at the fast RCNN and the faster RCNN. And it's like the fast RCNN is just like an improved version of the initial RCNN, where most of the upgrades concern speed. Advantages include higher detection quality as compared to RCNN and a single stage training using a multitask loss. no disk storage for feature caching, and more. And the faster RCNN is like a more robust version of the fast RCNN. And initially, the selective search algorithm was used in order to propose regions on an image on the RCNN. And on fast RCNN, they replaced the selective search algorithm by a convolutional neural network in order to perform the region proposal. So that region proposal network is basically a neural network, and it can be trained and it can be optimized. So this means that the algorithm computes the image with a wider range to generate more accurate results. So SSD is also another object detector, and it stands for a single shot detector. And it's one of the fastest real-time object detection models. It can achieve an astonishing 5 to 10-fold increase in speed compared to RCNNs by taking advantage of a multi-scale features and default boxes. So the SSD doesn't belong to the RCNN family, and it's also faster than RCNN because it's closer to YOLO. And one of the drawbacks of SSD is just in its accuracy, because it's not as accurate as our RCNNs. And another network is RetinaNet, and it was introduced in 2017, and it became one of YOLO's main competitors in the earliest stages of YOLO. And its architecture amazingly surpassed YOLO v2 and also challenged RCNN's accuracy. And it was increasingly being utilized in satellite and aerial imagery. So in order to sum up all the things that we have looked at in this video, is that YOLO is a recent object detector model, and it will still hold its special place for a number of reasons, because YOLO heavily relies on a unified detection mechanism that consolidates different object detection elements into a single neural network to effectively perform computer vision tasks. So YOLO models can be trained on a single neural network, and they're really fast compared to the RCNN family. And it's not surprising that the algorithm found application in countless industries, eventually becoming the nexus for projects invested in object detection.
Ago, computer vision researchers thought that getting a computer to tell the difference between a cat and a dog would be almost impossible, even with a significant advance in the state of artificial intelligence. Now we can do it at a level greater than 99% accuracy. This is called image classification. Given an image, put a label to that image, and computers know thousands of other categories as well. I'm a graduate student at the University of Washington, and I work on a project called DarkNet, which is a neural network framework for training and testing computer vision models. So let's just see what DarkNet thinks of this image that we have. When we run our classifier on this image, we see we don't just get a prediction of dog or cat, we actually get specific breed predictions. That's the level of granularity we have now. And it's correct. My dog is in fact a Malamute. So we've made amazing strides in image classification. But what happens when we run our classifier on an image that looks like this? Well, we see that the classifier comes back with a pretty similar prediction. And it's correct, there is a Malamute in the image, but just given this label, we don't actually know that much about what's going on in the image. We need something more powerful. I work on a problem called object detection, where we look at an image and try to find all of the objects, put bounding boxes around them, and say what those objects are. So here's what happens when we run a detector on this image. Now, with this kind of result, we can do a lot more with our computer vision algorithms. We see that it knows that there's a cat and a dog. It knows their relative locations, their size. It may even know some extra information. There's a book sitting in the background. And if you want to build a system on top of computer vision, say a self-driving vehicle or a robotic system, this is the kind of information that you want. You want something so that you can interact with the physical world. Now, when I started working on object detection, it took 20 seconds to process a single image. And to get a feel for why speed is so important in this domain, here's an example of an object detector that takes 2 seconds to process an image. So this is 10 times faster than the 20 seconds per image detector. And you can see that by the time it makes predictions, the entire state of the world has changed. And this wouldn't be very useful for an application. If we speed this up by another factor of 10, this is a detector running at 5 frames per second. This is a lot better. But for example, if there's any significant movement, I wouldn't want a system like this driving my car. This is our detection system running in real time on my laptop. So it smoothly tracks me as I move around the frame, and it's robust to a wide variety of changes in size, pose, forward, backward. This is great. This is what we really need if we're going to build systems on top of computer vision. So in just a few years, we've gone from 20 seconds per image to 20 milliseconds per image, 1,000 times faster. How did we get there? Well, in the past, object detection systems would take an image like this and split it into a bunch of regions, and then run a classifier on each of these regions. And high scores for that classifier would be considered detections in the image. But this involved running a classifier thousands of times over an image, thousands of neural network evaluations to produce detection. Instead, we trained a single network to do all of detection for us. It produces all of the bounding boxes and class probabilities simultaneously. With our system, instead of looking at an image thousands of times to produce detection, you only look once. And that's why we call it the YOLO method of object detection. So with this speed, we're not just limited to images, we can process video in real time. And now, instead of just seeing that cat and dog, we can see them move around and interact with each other. This is a detector that we trained on 80 different classes in Microsoft's COCO dataset. It has all sorts of things like spoon and fork, bowl, common objects like that. It has a variety of more exotic things, animals, cars, zebras, giraffes. And now we're going to do something fun. We're just going to go out into the audience and see what kind of things we can detect. Does anyone want a stuffed animal? There's some teddy bears out there. And we can turn down our threshold for detection a little bit so we can find more of you guys out in the audience. Let's see if we can get these stop signs. We find some backpacks. Let's just zoom in a little bit. And this is great. And all of the processing is happening in real time on the laptop. And it's important to remember that this is a general purpose object detection system. So we can train this for any image domain. The same code that we use to find stop signs or pedestrians, bicycles in a self-driving vehicle can be used to find cancer cells in a tissue biopsy. And there are researchers around the globe already using this technology for advances in things like medicine, robotics. This morning I read a paper where they were taking a census of animals in Nairobi National Park with YOLO as part of this detection system. And that's because DarkNet is open source and in the public domain, free for anyone to use. But we wanted to make detection even more accessible and usable. So through a combination of model optimization, network binarization and approximation, we actually have object detection running on a phone. And I'm really excited because now we have a pretty powerful solution to this low-level computer vision problem, and anyone can take it and build something with it. So now the rest is up to all of you. And people around the world with access to this software, and I can't wait to see what people will build with this technology. Thank you.